Okay, so just some housekeeping rules with the GoToWebinar tool. If you can hear me, you can type something on the chat window. If you can't, then the computer could be in a mute mode. If you can't see my screen, you can click on the maximize button in the GoToWebinar. You can hide the dialog box of the GoToWebinar using the red arrow as shown here. And the chat box can be used for any questions you have in the middle of the session, and you can pause me and I'll try to answer those questions. Okay, so today we'll be looking at varied number of bridges. We will start with just a brief introduction to the bridge analysis software that we are going to use for all these different types of examples. We'll start with single span integral bridges, both composite steel and composite precast beam type of integral bridges. We'll look at how to model them and analyze and design them. We'll also look at some important aspects related to multi-span curved composite steel girder bridges. And then we'll look at some special types of infill bridge decks, which will involve prestressed precast sections. Midas Civil, which we will be using today, is a bridge analysis and design software. It can do conventional bridge analysis such as slabs, culverts, frames, arches, composite girder bridges, which we'll be showing today, segmentally constructed post-tension box girder bridges, which involves different methods of constructions like the segmental or span-by-span construction methods, cable bridges like cable stayed and suspension bridges, and we have underground structures, and you can also do seismic analysis and detail analysis, which involves lateral torsion buckling analysis for plated girders. The design workflow for any kind of bridge that we follow in the software Midas involves creating geometry first of all and assigning them its properties. Geometry can be either created within the software or you can bring it from AutoCAD files. Basically, we call it the DXF file format. Boundary conditions, after defining all your geometry and properties, we defined boundaries, which can involve ideal fixed pin or hinge supports, or it can involve soil springs, some nonlinear bearings and releases, and etc. Load conditions, this involves your dead loads, your moving live loads, some temperature loads, settlement loads. We'll be looking at all these different types of loads in this basic training. Then construction stage, which is important for composite type of bridges. We can simulate the construction of the accurate construction of the steel girders being placed first and then the concrete deck casted after that. And there are other few examples of where the construction stages can be applied in the analysis. Then we perform the analysis and review the results, analysis results, which includes your reactions, stresses, beam forces, and deformations. And then we finally do the member design check within the software. We have got the steel and concrete frame design, composite steel, plate and box girder design, PSC design, and we can also do the rating design. Okay, so let's quickly move on to our first example, which we'll be looking at. It's a single span integral bridge. The major features which we will focus on in this type of bridge is how to model the deck, considering the skew and different types of skew, like if you have a skew angle less than 20 degree or greater than 20 degree, what kind of grillage you should be adopting. Composite steel bridges, which is on the left side shown here. We'll also look at composite prestressed precast beam bridge, which will include your precast Y-beams, M-beams, etc. Then one of the most important things with integral bridges is the soil structure interaction. We'll see how to model the soil springs for the piles and abutments. Then we look at composite action in construction stages, and also as per the Eurocode, we'll consider the cracked sections on the 15% span from either side of the supports. Okay, so quickly I'll take you to the software. do let me know if you have any questions. You can type on the questions window and I'll be answering it within in the session itself. Okay, so this is a completely analyzed model. I brought in this just to show you briefly where the different options are and how to find them if you are trying it for the first time, Midas Civil. So the way the software is built is it has the same interface as CAD package, like a ribbon type of interface where all the important menus are arranged in a form of a ribbon on the top. You can easily understand which menu refers to which type of feature, element, properties, boundaries, loads, etc. And this is the main graphical window. You can switch through different views just like in AutoCAD, top view, side view, and so on. You can browse through construction stages using this in this box here. You can call it the stage simulation box. And you can look at different types of how the construction is being progressed, how the deck is poured in different areas. We'll also use the works tree quite a lot. This is the place where the information for the model is stored. You can read through the works tree to find out what is actually going on inside the model, what kind of sections are used and everything. If you want to edit any property, you can just right click on the works tree here itself, say section, properties, and you can edit the properties. We can also drag and drop sections and materials from the works tree and assign them directly in the graphical user interface, which we will be seeing in the examples. Then you can also look at tabular data entry, like notes table, for example. Again, these are Excel compatible. And then you have a message window here which displays some warnings or errors if you have committed any mistakes in the model. And a command line is here, so you can type in commands like create elements and similar commands like that. It will prompt you towards the nearest command. Okay, so I will open up a new project. So just go to Midas Civil, just open up a new project. So that's the Civil 2014, which has been released this week. So we go to File, New Project to start up a new project. Okay. You can see the coordinate system here. X, Y are the horizontal axis, and Z is vertically up, and it follows the right-hand rule everywhere in the software. Okay, so how do we start modeling a particular bridge? There are different approaches. You can. Some people prefer to use AutoCAD, bring in a model from AutoCAD. Some people try to model it from scratch. We'll see both of these approaches. So let me first show you the how to import a model from AutoCAD and what kind of precautions you should take while importing. Okay, so here is import AutoCAD DXF option. So first of all, it should be a DXF file, not a DWG file. Okay. And we browse for the AutoCAD file. So browse, let's say it's saved here. So that's the file which I want. Now the next thing is make sure that the unit system is same. So it gives you a warning when importing AutoCAD DXF file, the length unit should be identical to the units in AutoCAD. So to change the unit system, there is a very quick way of doing it. There is an option in the status bar. You can just switch between different units, say millimeters. And you can select the layers which you want. So say I just select everything. Here assign some default materials or sections, whatever it is. Click OK, and you've got an integral bridge. So how was this modeled in AutoCAD? I'll just explain to you. So all these beam elements which comprise the composite steel girders, they should be modeled as lines. So nothing should be polyline in AutoCAD. And then you have the piles. Again, they should be lines with all the required intersection points already made in AutoCAD. And these shell elements which represent the abutments, they should be 2D or 3D face elements in AutoCAD. So if these parameters match and the unit system matches, then you should have absolutely no problem in importing the model from AutoCAD. So that's how you import the model from AutoCAD. You can then start assigning some properties and sections by selecting the different members. So I won't go into that part. because I'll show you another way of modeling which we generally follow, that is modeling from scratch, and you would definitely get an idea about how easy it is to model from scratch. So I'll click on new project again. I don't need to save it. Okay. Right, so I'll start with first of all a simple node at the origin. So I'll use the node element command, create nodes 000 and apply. So a node is generated here. Now I want to model a skewed deck. So what I will do is create a transverse line which will represent the reference line for the skew. So I'll use this node, select it. The selection tools are similar to AutoCAD. So selecting this and extrude, say just enter how many divisions I want on that skew, on that line. So say in the Y direction, say 4 at 3 meters, for example. Apply. Okay, and select all these, and now I'll rotate it to create the skew. So I'll go to nodes again, rotate nodes, and just say move, intersect. Now here you enter the skew angle of the bridge of the deck. So if your integral bridge is skewed, let's say minus 15 degree in the 15 degrees in the clockwise direction, so minus 15. And about z-axis, select the axis point and apply. So that's, you got the skew line now. Now we can create the main girders out of these points using the same option of extrude, but this time use the x direction. Say we have a 40 meter long span, so apply, and that's it. We have got the span information now. Now what we're going to do is apply. We'll copy this transverse member on throughout the length of the bridge to create the grillage. Now since the skew angle is less than 20 degrees, we can go for an inclined transverse type of grillage. If the skew angle is greater than 20 degree, which we will see in later on in another example, then we have to go for orthogonal grillage to correctly represent the transverse and longitudinal behavior of the deck. So keeping that in mind, I'll since this is just a inclined or transverse grillage, no, there is no orthogonal grillage here, so I'll just simply copy this along the length. So the beauty of using the starting from scratch in Midas is that it's exactly it gives you the feel of using the CAD package itself. So I can measure the distance directly by clicking on start and end nodes, and say I want for example 20 transverse members. So I divide the distance by 20 and say 20 times and intersect node element and apply. So you will see that nodes are generated at every intersection point, and you've got the grillage model, grillage deck completed. So now we can focus on the abutment and piles. So again, modeling the abutment is fairly easy. So we can simply select this part of the transverse member. So using the polygon option, just create a polygon like this, and use the extrude function again. This time we'll create planar elements out of lines, and in the Z direction, say our abutment is 4 meter high or deep, so we can give a division of 1 meter in 1 meter intervals 4 times and apply. So you've got the abutment here, and then using the abutment nodes we can model the piles as well. So simply just copying here and changing this to node to line, and say normally we have the soil profile for the pile at every 1 meter interval. So we know how the subgrade reaction changes at 1 meter interval from the soil data. Because soil structure interaction is very important for the integral bridges. We therefore have to consider a good amount of accuracy when we are doing assigning the soil springs. So what I'm trying to do is keep or divide the piles at every 1 meter intervals and assign soil springs to it. So -1 in the Z direction and say 11 times. So it's a 11 meter deep pile. Maybe make it 20. So it will be, because the length is 40 meters. So it will be fairly good enough. Okay. All right, so I haven't defined any sections yet, any material yet. So let me just go to the properties definition and quickly define some materials and sections. Okay, so I go to properties, material. I can add a material, steel, concrete, or user defined. So for the design of composite sections, I should go for composite material. I need to specify steel and concrete. Just name it composites so that it's easy to identify. Apply, and then maybe go for steel and probably S355. Apply, and then concrete. So this concrete material is for the piles and abutments. So I'll just type in piles so that I can identify them. And I'll type in another material for the slab, for the transverse grillage members. So I'll just type in slab here, slab transverse. Okay, and make sure it's C35. Now for the transverse members, I don't want to consider any weight density, so I'll keep it, bring it to none and change the density to 0 and apply. Then say for example, I want to consider I want to have a material for the concrete longitudinal concrete parts so that I can consider the time dependent effect like creep and shrinkage, which we will also see later on how we can consider them along with the composite action. So I'll create a material for the slab. Again, I don't want to include any density for even the composite slab part, because I will be applying the density as a wet concrete load. Because the steel girders, when the steel girders are casted or installed, they will have the wet concrete load already acting on them. So we need not consider weight density for the slab separately. So that's why I'll keep it as 0 and okay. Now we could have imported all the materials from a previous model. So I just showed all the materials here. Now for the section, I'll go to the section tab, add, and you can create multitude of different types of sections, starting from standard sections like I sections. You can select British standard and select different U-beams and universal columns. Then we can also go for composite sections where you have steel I or composite PSC, which is composite precast sections. So instead of modeling each and every section, I'll just import it because it's fairly just simple, adding some dimensions and everything. So I'll just, to save time, I'll import the sections. And I've imported it from an already generated model. So it should have all the sections here. Right, so if you see on the screen, all the elements have been assigned with the same section property. You can see in the works tree that some of the materials and sections are in blue and some are in black. The blue ones indicate that you have not assigned them to any element yet. So we can also double click and check which has been assigned to in the structure. Okay, just pause and try to answer a question here raised by one of the attendees here. So the question is that how to import the arcs or curve type of elements. So yes, the one way is that, I mean, you cannot import splines or arcs directly, but you can break them into lines, into further segments, and import them. Sometimes you can also use polylines, but I would not recommend using polylines every time, because polylines can have some problems with the intersection. It is always good to use lines whenever you have to generate the arcs or any other type of geometry. So always break your arc into several segments and import them into Midas Civil. Because the software directly deals with mesh, there is no so-called geometry involved, and you will get to know the reason behind it, because the options available for geometry modeling are fairly simple within the software. So you can directly create the mesh as if it resembles geometry itself. So I'll go through some curved geometries as well in this example. We'll look at curved bridges, and then I'll cover the aspect of how to model horizontally curved bridge. So I hope that answers your question, Riza. Okay, I will now go towards assigning the properties correctly, because everything has been assigned with composite section. So here we just have to select the correct elements, drag and drop piles, double click on piles again, drag and drop piles materials. Similarly for abutment, make sure that everything is abutment material, which is pile material. I haven't defined any thickness for the abutment, so I'll just define 1 meter as a thickness, and that's how we define the abutment and define the sections and the materials. Now for the transverse members, I'll just switch on to the wireframe view. For the transverse members, I'll quickly select all the transverse members here and drag and drop the transverse property. I've defined them as dummy sections because I have entered the properties manually. We have a value section option in the software where you can manually define any property for the shear areas or moment of inertia for the transverse members. So I'll go to view and use the intersect line option. Just intersect few transverse elements like this, right? And drag and drop dummy, double click on dummy, drag and drop slab transverse elements. And let's see how it looks now. So it seems it's been correctly assigned. Now you might have one question that the alignment of the deck, how come it's it's exactly flushed with the abutment top? So the reason is that there is an option in the section property itself where you can offset the section. So if I define a section, there is an offset option which allows you to offset the sections by or set them to some extreme fiber. So if I select center top, that means the reference line will represent the top fiber as shown in the figure here. So you don't have to worry about applying a link separately to connect the top with the center line. Okay, so I've defined the section properties. Now I will go for the taper sections. We have taper sections at the ends here. So what I'll do is activate just the composite beams. So these are the composite beams here. Now just switching back to the top view and close this view. Okay, now taper sections are very simple to generate in the software. You just have to create two sections first at the start and end, and then just tell the software which section you want at which end. So normally the ends are represented by the terms I and J. So if I say size I, which means at the start maybe composite girder 1, and start J maybe composite girder 2, and that's how it interpolates the section properties and gives you a tapered section. So I will select a few elements here. So let me select, for example, these many elements. Okay, and assign them with tapered, drag and drop. Let me check the shape from the front view. Yep, so that's the type of section that I want, but of course this is this has been divided into discrete sections which I have to rectify, so I'll come to that thing in a couple of minutes. So I'll select this part and taper to. Okay, now I need to correct them properly, so I have a parabolic profile for the tapered sections. So I'll just go to properties, tapered group, and just give a group name, say tapered 1, and element list, probably open up another works tree here and double click on tapered. Polynomial, which is allows you to give a parabolic profile. Okay, and let's see, so we want parabolic, so polynomial with degree 2 and add. Oops, that's the other way around, so change it to J, modify. So now you have a parabolic profile. So software has interpolated the values. Now similarly for taper 2, okay, make sure everything is unselected and then select taper 2 and add. Okay, so we have got the correct profile here. Now Eurocode also says that the 15% span on either side of the supports should be considered as cracked, so the fully cracked deck. So we need to do that. So I'm assuming that the first 4 elements here on each girder, they should be cracked, but you should always have a node representing the 15% span so that you can identify which sections you want to crack. And also you need to define those sections separately with a different name. So right now, coincidentally, I want the tapered sections to be cracked, so they are already separated out from the main sections. You can see that's the main section highlighted, tapered 1 and tapered 2. So I want tapered 1 and tapered 2 to be cracked. So I'll go to properties, section manager, and go to reinforcement. So in the reinforcement option, you have to enter reinforcement for the cracked part so that the software can consider stiffness for the reinforcement only. So I'll select composite girder, that's the main span, typical section. So I'll say give some cover, 0.05 for example, and just simply draw 2 lines representing the line of the reinforcement. Just say this one and say 20 bars I want, add. And similarly do this for the top and add. And here you can specify cracked, but we don't want the mid section to be cracked, so I'll apply and go for the tapered section. So here repeat the process, just model it like this, just doing some arbitrary reinforcement. So because these reinforcement will also be considered in the design check as per EC4, Eurocode 4. So you need to carefully enter them as the reinforcement which you actually want for the deck. So now if I check on cracked, the software will consider the deck stiffness to be 0. So only the reinforcement and the steel will be used for analysis. Okay. Okay, so that's entered. Now we need to model the soil structure interaction. So I'll activate everything now and show you how to do the soil structure interaction automatically from the software. So we'll go to boundaries and go to integral bridge. We have different ways of applying soil springs. So if you want to manually apply soil springs, then you use point spring option. You just select a few nodes here and there and assign the stiffness value in 6 directions. So that's the manual approach. I'll go for the inbuilt empirical based approach for integral bridges. So that's the integral bridge supports. So we have 2 types of springs which we need to consider for the integral bridges. One is the abutment springs and then the other is the pile springs. The abutment spring is crucial in cases if you want to consider the fatigue in the backfill, the effect of soil structure, because when you have thermal and thermal contraction and expansion in the deck, the abutment along with the deck moves. So there is a constant separation, or you can say the backfill constantly undergoes a fatigue, like a cycle of expansion and contraction in the deck. So this effect should be considered in the soil structure interaction, and the term for this will be strain ratcheting, and you can consider this in the software just by simply selecting few abutment elements. So I'll just select few of them here. Abutment spring, and if you have a strip footing below, you can also select the nodes representing the strip footing, but we don't have a strip footing. Abutment height, that can be simply calculated. I'll just save this model. So abutment height and width, that's the width, and deck length. So I'll switch to the view. So you can see most of the places you can measure the distances directly from the graphical user interface. Void ratio, this is something you get from the soil data. Cycle factor, this is the factor that considers the fatigue. I will show you the basis for this, the empirical formulas required for this. Thermal expansion to be considered, say 20 degrees, and the material of the abutments, piles, and apply. So that models the springs for us. So these are nonlinear horizontal springs, compression only springs. So it will automatically take the effect of your active and passive pressures in the backfill. So that's the spring you have, compression or tension only. You see these are compression only springs with some stiffness. The stiffness has been calculated based on the paper by B.M. Lehan. For more information, you can go to just the help file and go to boundaries, spring supports, integral bridge, and you can find a full description of how it's been calculated. The same thing we do for the piles. Now this is where the 1 meter division comes into picture. So normally the soil profile is given per meter basis. So we select pile spring and select the soil type, say sand, soft clay, or stiff clay. Go for sand. Ground level, specify the ground level here. Pile diameter is say 1 meter. Coefficient of subgrade reaction, this is from the soil data. So say 30,000. And select say top 5 or say last 5 meters are last few meters are sand, for example. Apply. Then clay, say top 5 top few elements are clay, and apply. So that's how the software calculates your nonlinear springs. So if you see the properties, they are all nonlinear springs. So based on the loading applied, the stiffness will vary, and you will get the good soil structure interaction for the integral bridge. Okay, now this can be also done in a parametric way. So you can do similarly short-term springs and also do a long-term springs and consider them separately in a construction stage. In the same model, you can consider them on separate load cases and check the short-term and long-term effects. So I'll not go into that detail. You can, I'll just now show you the application of loads and how to develop the construction stages. The same principle will be followed in our next few examples. So I'll just show you for this particular example, and we'll just see some other features for other pertinent examples. Okay, another of our user attendees has asked a question that if the taper section is not a linear transition, as I showed here, the taper sections can be any shape. It can be linear or parabolic. It all depends on what kind of polynomial you select. So it can be anything. You can select, go for cubic, go for linear, parabolic, anything. Going back to the demonstration, I'll first of all copy the abutments on the other side. So just use the polygon selection and node elements, translate, and just copy it simply by measuring the distance like this. Now, while you're copying this, the abutment and piles, we can also copy all the attributes associated with it. That is, all the links and supports and springs or any loads that are being applied on the support. So, apply Let's check. So it should have copied all the springs. You see, all the springs are now copied. Okay. Now we need to make sure that the springs also have the correct direction, because we included the compression only springs for the abutment. So for the axis, the local axis of the abutment should be opposite to each other in order to simulate the compression correctly. So in order to check the local axis of the abutment, we can turn on the local axis here and look at the local axis of all the elements. So you see Z is the normal local axis of the plate, and they are, for both the abutments, they are on the same, pointing in the same direction. This can have this can result in incorrect pressure load on the due to the backfill on the abutment. So we need to reverse on one of the plates the local axis. So I'll just highlight the plates and press the activate button and just select this particular abutment here and reverse the local axis. So elements, change parameters, reverse element local, planar, and apply. So now these are reversed, and any loads that you applied normally will be applied in the opposite direction. So speaking about loads, let's go into that part of the presentation. So first of all, we need to create some groups if you want to consider loads in the construction stages or elements in the construction stages. So we'll start with making some groups. I'll just switch off the local axis, okay, and go to structure group, new, right click and press new, and we can save substructure. So the way the construction will progress is that substructure will be activated first, and then we'll have the steel girders placed, and then we'll have the transverse grillage, so transverse members. Similarly, boundary groups, we have only one type of boundary, which is soil springs, so just one group. And load groups such as self dead load of girders and substructure, so I just simply write it as self weight. Then wet concrete, and then earth pressure. So sometimes what we do is, instead of modeling the boundaries for the abutment, we don't go into the abutment soil structure interaction. Rather, we apply the pressure on the abutment on both the abutments and ignore the boundaries. So that will be that is also another way of applying earth pressure and say surfacing. Okay. Now quickly I'll assign to groups different types of elements. So I'll start with the piles and abutment first. So just quickly copying all the piles and abutments and drag and drop substructure. All the steel girders, so double click on double click on the composite material and drag and drop steel girders, and double click on slab transverse, drag and drop the transverse members. Then select everything, drag and drop soil springs to include all the boundaries in the structure into soil springs group. And for self weight and wet concrete, we'll see when we apply the loads. So we'll create some load case names. Self weight, that's your applied in the construction stages. So I'll say construction stage. The type is important because the software has the capability of applying the load combination factors automatically based on the type, based on the Eurocode or any other standards. So then comes wet concrete. Again, this is construction stage. Surfacing, you can apply it in construction stages. Earth pressure, this can also be applied in the first stage when we have the abutment, so let's keep it in the construction stage. Then there are some other loads like uniform temperature. This is temperature load, so temperature. And you can similarly create temperature difference, temperature gradient, add. Let's go for these cases and quickly assign some load values. So starting with self weight, select the group name self weight, -1, which is the gravity direction. Close this. Then we go for wet concrete loads. Wet concrete load will be applied manually on the steel girders, so they will be acting as a UDL, uniformly distributed load. Wet concrete, and you can type in some mathematical function here. So say 25 times the 0.3 say into 3, which is the width of the slab, effective width of the slab, and double click on composite and apply. So that's the wet concrete load applied on all the girders. The next thing is applying surfacing loads. So surfacing, we can select some of the internal beams and apply surfacing loads. So you can apply surfacing as a floor load as well. Depends how you want to consider it. You can apply it as a UDL. So I'm going to apply it as a UDL in this example. So just selecting, say, these many girders and -10, for example, and apply. And then we'll apply the abutment loads as well. So right click on plates, active, hydrostatic pressure, that's the earth pressure load, earth pressure, and reference height is the top, starting with 0. Intensity should be the unit weight of soil, so keep it 19, for example. Apply. So minus is just for the direction. You can, because it's in local Z, in the reverse direction of the abutment local axis. That's the backfill pressure applied. Okay, now similarly we can apply the temperature loads. You can go for element temperature, select all your elements, or select only the deck. Let's select only the deck. Composite, uniform temperature, give some temperature values and apply. Okay, there's one question here regarding the surfacing loads. So actually, while you're applying the surfacing, you should always apply it on the correct part of the carriageway of the deck. So here I just applied it arbitrarily on the girders. So actually you should have, if it is a grillage model, then we can go for some dummy beams modeled here, just to represent the extent of the loading. So you can create some dummy beams in between with some little stiffness or smaller cross sections like 10 millimeters by 10 millimeters, for example, and just apply the loads as a floor load on those members. So just to show you what I mean by a floor load in the software is just going to floor loads, floor load type. First of all, I define surfacing, say -4 kilonewton per meter square. Say this is surfacing. Sorry. Add, and say I want to load the area in here. So I go to assign flow loads option and just select a two-way type of distribution. You can go for one way as well, so only the main girders will be loaded. And just select the nodes, outer nodes of, so if you have dummy beams on the outline, you can select the nodes on the dummy beams. So I'll select the nodes somewhere here. But for doing this, you should have an enclosed area. So something like this will appear up. So the pressure load is distributed, the flow load is distributed in a two-way fashion on the enclosed area. You can have dummy beams and dummy beams here on all four corners and just use them for loading. So just select the outline going like this and it will distribute automatically. Or the other way is you can also, if you know the distribution on each girder, you can also manually apply UDLs on the main girders itself, because it will be more conservative that way if you apply the surfacing directly on the main girders. So it's up to you which approach you want to consider. Sometimes you can also model a dummy plate on the slab and go for patch loading. We have the patch loading option here, which allows you to load any part of the plate. You need not have a node there, existing node there. You can add a load in between a plate. So there are different options, but normally for a grillage model, we don't go for modeling the dummy plate because it makes the modeling. It kills the analysis time because of extra plate elements. So it's you can choose the dummy beam approach for loading. So now I'll go to the construction stages and quickly define the construction stages. So I'll go to start with the stage 1. Stage 1, which says substructure. This is a stage which has duration, say 28 days. Substructure, you can give some age or you can ignore it if you don't want to consider creep and shrinkage in the substructure. Boundaries, soil springs will be there, loads, earth pressure will be there, and self-weight will be activated from the first day itself. Apply. Then stage 2, this will be the stage where steel girders are there. So just say 7 days, for example. Steel girders need not need any age for steel girders, no creep and shrinkage. Wet concrete load, this is something which you can activate within a construction stage, say midway of this construction stage. So if it's 7 days, I can start applying the wet concrete load on the 3rd day, add, and select, and say select 3 here and add. So wet concrete load starts acting on the 3rd day. So at the end of the stage, the concrete will be 4 days old, and then when we activate the concrete, actually we should have the age as 4 days, just to correctly simulate the creep and shrinkage and elastic modulus effects. Apply, and then stage 3. This can be kept as a long-term effect stage, say 1000 days, and include transverse members here. So the deck is already composite now, and you have grillage members activated. So everything is in here. Surfacing can also be added from the first day itself, or maybe again create another day interval here, 28 days, add this on the 28th day, modify, and click OK. Okay, now we'll create the composite parts. So now the software doesn't know how to differentiate between different parts. So we add and go for composite girder section. We'll just check if yep. Right, so add, and stage 2, that's the stage when the steel girders are first placed. It's composite girder section, which is this one. Select material, steel, part 1 is steel as per the figure. Stage 2, age doesn't matter for steel. Material, slab. Now here we enter stage 3 because we want the slab to be composite on stage 3. Age should be 4 days. And that's the notational size automatically calculated by the software. And if you want, you can also vary the stiffness of the slab manually. So that's the stiffness calculated by the software, and scale factors can be added here to consider, say, partial cracking or some other types of situations where you want to vary the stiffness. So click OK. So you need to do the same thing for the taper sections, but I'll skip that and show you how the stages look. So that's the first stage. Just switching on the view here, hidden view, and you will find that point spring supports are there, self-weight is there, and earth pressure is there. Then you have stage 2. You see the middle portion, because we separated the deck and the steel, it is being shown graphically as well, but the tapered ones are not separated out, so we need to do that. So that's how stage 2 goes. Stage 3, we have got the complete composite deck along with the grillage transverse members as well, with all the loadings. So that's how you do the construction stage analysis for a composite bridge. Then the next thing is applying creep and shrinkage, which is fairly simple. You go to properties, creep, shrinkage. Sorry, creep and shrinkage, add and select the code, say Eurocode, says creep, and define the model, the strength of concrete. Make sure it's in the correct units. That's it, and click OK. That's the creep curve being considered. Then we can do that for compressive strength. So that's the elastic modulus variation of concrete based on this the values which we enter here. So like this. So this will be the elastic modulus variation, and you can consider them in the construction stages. And then link the two time functions with the correct property with, say, slab. And wherever the slab has been used in the model, creep and shrinkage or compressive strength again will be considered. Okay, then we go into the moving load or live load analysis. So I'm showing you this on one model itself because the process is the same on all other models that I'll be showing. So I'll just go to moving load analysis, loads, moving load, and you can select Eurocode. So go for traffic line lanes. Okay, so traffic line lanes, add, so give a name to the lanes, say remaining area 1. So we need to define which are the remaining areas and which are the notional lanes. So -1, say 2 meters is the width of the remaining area lane. Distribution type is via the cross beams or the transverse beams. So whenever you have a grillage model, you have to select the cross beam type distribution so that the load is accurately applied on the transverse and the longitudinal members. If it is a line element model, like if you have a post tension box girder, then there is no cross beam, so you have to go for line element type here. So it will be applied directly on the reference. The loads will be directly applied on the reference beam. This is where you enter the skew angle. So I'll enter 15 degrees and 15 degrees start and end of the deck. And there are different ways of selecting the reference line. So either you create a start, just click on start and end points. Okay. And click apply. So you will see remaining area lane is generated. You can also select the elements. So in case of curved bridge where we can't easily select the start and end point, in case of curved bridge we just select all these elements on that line and just tell the software the element number. So we'll look at that in the curved bridge example. So that's our remaining area 1 applied. Now we'll apply lane 1. Lane A, sorry, because we don't know which one is notional lane 1 or 2. So we go for -3 meters, for example, and wheel spacing 3 meters. And just simply apply like this and apply. So that's lane A. Then we have lane B, -6, for example. Delete everything, add, sorry. And click OK. We can similarly define several other lanes and put way lanes and consider the moving load analysis. Now, the next thing is applying vehicles. So you can add standard vehicles like load model 1. You can input the adjustment factor as per the national annex. So I'm just entering something similar to the UK national annex. And some psi factors apply. Load model 3, UK national annex, which involves special vehicles. Select SB196, for example. Click apply. And several other load models are there based on the type of bridge, like rail traffic load for railway bridges. You can also go for user-defined vehicles. So any type of abnormal vehicles can be defined, like having 4 axles or varying axle spacings. All those things can be defined in the moving load analysis. Then we create the groups of combinations. So go to moving load cases, add, and first case is the group 1 combination. So let's say GR1A. For the first group combination, we generally ignore the psi factor and select the lanes, select the remaining area lane and apply. Then we can also do the group, say group 5 combinations, which is load model 1 and 3. like this, load model 1 and 3, and we can specify the straddling lanes. So the special vehicle can have transverse variation of the axle wheels. And that's okay. So that's how you define the moving load analysis. You can give your own points of interest. Say if you go to analysis moving load, we can set the analysis to run for a set of elements only. For example, I want the effects of live loads only on my steel girders, so I can select steel girders here and run the analysis for the steel girders. So that's how that's in a nutshell how you define model and define all the loads and geometries and boundaries. So now I will show you different scenarios like curved or when you have precast beams, what other types of loads you need. The rest of the procedure is exactly same as what you have seen here. So we'll now go to the another example of this time a precast composite bridge. Okay, so actually what I'll do is within this example itself I will modify my section. We have another question related to the live loads. The question is that does it matter which reference beams we use as our starting basis for defining our lanes? It does not matter as long as you have defined the cross beam type of distribution. You can use some other lane and define some different eccentricity to match the correct position of the lanes. So as long as you have defined the transverse information that you want to apply the loads via the cross beams, it gives you the same results for any reference beam. There is another question. The vehicle load to be for the case of special vehicles where we have straddling. The lane width is say 3.6 meters and the wheel spacing is 2 meters. So actually for the straddling vehicles, what happens is if you specify 2 lanes between which the vehicle will straddle, the software creates multiple internally it creates multiple lanes between those 2 lanes and places the vehicle on different lanes with the 2 meter spacing, and then gives you the worst effect. So it does vary the transverse distribution of loads in that way by considering different lanes. So you get approximately the same effect as you would have got by varying the wheel spacing of the vehicle itself. So now I'll just modify the section type to composite precast section. So go to add a new section, PSC prestressed concrete, a value type section. Now we'll select a section from the database. So we have got a database of predefined precast sections. So we'll select TY section, yep, this one, and say TY8. Okay, so that's the default section. Just give a name, say TY8, and section and other parameters for the design. This is not important for analysis, so we just enter some parameters for the design which involve your top flange, bottom flange information. 0.4. And just specify some position for the shear check. So say 0.8, sorry, 0.7, and 0.3. So these are the lines where the shear stress check will be done. Okay. Okay, and just click OK. And we now select another section. This one is a composite section, composite precast. So make it composite precast, and slab width, effective slab width is 3 meters, 1 meter here, 1 girder per slab, 3, and spacing is, the width thickness is 0.3 meters. And we select the TY8 section which we just generated. Select the material for the slab C40 and for the girder 50 for example. Click OK, and again the offset is center top. Okay, so what I'm going to do is quickly drag and drop the composite precast section. So may not be the dimensions, will see the dimensions are not exactly matching because the section size is too small, but anyways the objective of this exercise is to see how to quickly assign pre-stressed tendons and how the software can do the loss calculation for the tendons, and you can get the ULS effects for dead loads and tendon pre-stress. So I will just activate the precast section. Okay, so those who have been using the 2013 version of the software, there is a new development in the 2014 version, which is the predefined tendon templates. So for any given precast section, we can just simply select the tendon template here. So I've selected this option and select the members that we want to assign the pre-stress with. So maybe turn on the line view, and it's good to create groups for each girder. So that's the girder selected. You can see the section view. Now we use the auto generate function. Of course, we need to define a tendon property. So I'll just quickly define one. So it's an internal pre-tensioned strand. Tendon material can be specified with the correct material of tendon. I've just specified a steel material. Number of strands and strand diameters. So I'll just select strand as 15 millimeters strand. And what is the relaxation coefficient? Eurocode ordinary steel. And OK. And close this and click OK. So as soon as you auto-generate this, you will find the tendons are applied automatically based on the database. We have got an inbuilt database of all the different types of precast sections and the tendon profiles. Now you can manually select some of them and mark them as debonded. So if I select, say, this particular tendon, go to modify and give some horizontal offset, which is the debonding, say 2 meters and 2 meters, like this. And you can go for a varied number of shapes. So for engineers who are using Midas for post-tension box girder sections, this particular wizard can be used very easily for the parabolic tendons and for other types of draped tendon profiles, something like this. So in this example, we'll focus on straight only, and just cancel and reselect that again. Yes, so that's 2 meters and 2 meters here. Span length is auto calculated, so click OK, and that tendon is now debonded. We'll select another one from here and just modify. Sorry, select this, modify, and just say 2 meters from the start, 2 meters from the end. Okay, and so that's it, and we click apply to assign the tendon correctly. Then similarly, we select the this other the girder. So maybe switch to the side view and select like this. Apply. Let's view them. So display, and you can see how they have been applied. I'll just remove the tendon names from the display and display only the tendon points, and maybe hide the abutment so you can see it more clearly. Okay, so you can see the tendons have been correctly applied here. Now for applying the jacking force on these tendons, we can do the same thing for other girders as well. We have a copy function, and we can also export the current tendon profile into some other CAD format. So I won't go into that detail. I will just show you how we can apply the jacking force for the precast beams. So we need to create a load case name. We go to load, static loads, static load cases. Say this is pre-stress. Type is again, construction, if you do want to do construction stage analysis, we can include it under construction stages itself. And just apply jacking force from here. Select pre-stress. We need to have a group as well as we created for other loads. So pre-stress, add, close this. So pre-stress, select all the strands which we want to pre-stress, and jacking from which end, both ends for example, and apply it as a force. So say 250 and 250 kilonewtons for each strand, and click add. So that's how jacking force is applied. Now when you're doing the construction stage analysis for the composite precast bridges, it's exactly same in terms of generation of the stages like the composite steel bridge. The only difference is that we just need to add a pre-stress load group in the first or in the stage when we activate the precast beams. So say the precast beams are activated with an age of so this is the precast beam. We can give an age now because it's concrete. So we can give an age, say 7 days for example. Considering that pre-stress is applied at age 7, so that's why I entered 7 days to consider that the transfer of the pre-stress. Then we can apply pre-stress on the first day. So when concrete age is 7, the pre-stress is being transferred. Okay, and that's how it will be considered gradually. So most of the cases you can just keep it as 28 days, which will be the full strength of the precast beams. But you can also go for little conservative by taking into account the losses in the initial losses in the precast beams itself. So then it's considered from the parts are considered separately from this option, where you specify members, the materials for girders and materials for your slab, and the age for both of them, and creep and shrinkage will be considered for both the materials. So that's how we do the precast concrete bridges. One of the questions is, can we use 30 days age? Yes, you can use 30 days age. As I said, most of the cases we apply the precast beams with the 30 days age because they have already attained the strength. But sometimes if we want to go for a little conservative approach, if you want to also incorporate the pre-stress transfer effect, the losses at the time of transfer, then you can input the correct age at the time of transfer. If the stage is 7, say has a duration of 7 days, it just means that the number of days that are will be involved in the analysis for this stage. The age of concrete is different from the stage duration. This is the age when you on the first day of this construction stage. So if I say the number of days here is 7 and I apply substructure with 5 days for example, then that means age of concrete on day 1 is 5 days, and on the last day of this stage will be 5 plus 7, 12 days. So that's how it keeps on adding the ages and gives you the creep and shrinkage effect for each age of concrete. Okay, so let's move on to the second part, where we'll look at the briefly we'll look at the curved girder bridges. We are slightly out of time here, but I'll try to finish it up quickly with some relevant examples and features for the curved bridges. Okay, so this is the bridge I'll be looking at, the 2-span composite steel girder bridge. So the important parts for a curved bridge is first of all the modeling of this bridge. If you're doing a grillage model, then how to model the curve, the horizontal curve, and how to automatically or quickly consider the transverse members instead of drawing them each and every one of them by hand or in AutoCAD. That is the first part. Then pouring sequence is very critical for multi-span composite steel girder bridges, because they determine the way you pour the way you start pouring the deck on the steel determines the locked-in stresses in the steel and also the deformations during the construction stage. Then another important aspect is the cross bracing involved for the curved bridges for providing stability to the steel girders. So we generally provide cross bracings at certain intervals along the span, and provide lateral stability to the girders. So I'll go to the software now. Okay, and look at the modeling part. So how to model a curved bridge from scratch. So create a node again, apply, select this node, and this is going to be the center of the curvature. So this is center, and go to extrude. In the X direction, so define the radius. So our radius of curvature for the center line of the bridge is 100 meters, and we have longitudinal beams at 3-meter intervals, and apply. So that's how these are the locations or the points from where we'll create the longitudinal beams. Now we'll rotate this these set of elements at equal intervals. So go to rotate elements and copy number of times, 40 times at 2-degree increments, and that's the axis of rotation, and apply. So we have got the relevant points for the curvature, and then we just use the arc method, line elements on arc. So arc by 3 center and 2 points, center and 2 points. Select the center, select number of segments as 40, and click here. So similarly do the same thing on this part. Sorry. Okay. So you can see how quickly you can draw the grillage for your curved bridges just using the arc function. And now once you're done with this, you can simply delete these elements. You don't need this, and start assigning your properties for the bridge. So that's how the geometry is modeled. Now let us look at the pouring sequence, why the pouring sequence is important. So I'll open up the analyzed model. Sorry. Okay. So that's the completed bridge, and let's see stage by stage. Let's just hide the nodes. So that's stage 0, which is having only steel girders, and you can see some cross bracings are also there. Stage 1, which is the first pour of the deck. Okay, so the grillage members, transverse members are only activated up to this stage. So how do we ensure the composite action? Well, we first have to make sure that we have nodes we have created nodes or divisions at every pore region, boundaries of the pore regions, so that we can assign those elements in a particular pore region with a given section name. So like I have named the section composite section based on the pore names. The other important thing in curved bridges is that you should also create intervals whenever there is splicing to get the splice forces. So that's why you can see the nomenclature that I've used here is based on the splicing information. So if this is girder B, then I have splices at 7 locations, and I've named them separately. And each pouring sequence has been named with different composite sections. So they can be the same section, but just name them differently. Why I've named them differently? Because then when you're assigning the parts, when you're differentiating which is steel and which is concrete, for example here, you can actually say girder number A, port 3, you want to activate steel in stage 0 and activate concrete in stage 3. Whereas for some other member, say port 5, port 5, maybe cancel, maybe here's port 4, for example. Yeah, so you can say stage 4 and so on. So that's how the stiffness will vary. That's how the software will consider steel and composite, steel only and composite section at different time intervals. So that's one of the most important things to be kept in mind while doing the pouring sequence. And the cross bracings, to model these cross bracings, I'll go back to the model here and just quickly open up. Okay. Okay, so I've got the cross section here. To model the cross bracings, we just need to select the nodes here, drop them below, so translate them in that direction. So come on, 5. Okay, this one, apply, and we just need to connect these with rigid links. So that's your master node and rigid body. That's a slave node. Apply. Do this for here as well. Apply. And say I can then these nodes are now part of the same beam now because of the rigid connection, and I can just simply model using any bracing section. You can just draw the bracing like this. So normally bracings will not intersect, so I'll check off the intersect option and just overlap them like this, so there is no intersecting nodes here. So that's how we model the bracings. For modeling the abutment and the pile cap here, we just need the outline. So if we have the nodes as shown here, okay, we can model the outlines, something like this, and maybe connect these. We can have a node at the bottom fiber of each steel section and connect them with bearings. So using these nodes of the abutment, we can extrude them in the downward direction. 4, let me apply, and then create elements, dummy. So that's the abutment section. Now we can create the pile caps as well. So just okay. So just where you have the at the plane of this abutment base, you can create a user coordinate system. So structure user coordinate system, 3 points, say like this, and click OK. And simply using the extrude function, you can create nodes and elements to define the outline. Now once you have the outline, let's say you will have the outline in this manner. So you'll have the outline like this. So we would like to mesh the entire thing. So that's the abutment shear. I'll delete all the free nodes if there are any using this option now. Okay, so to mesh this entire area quickly, we can go for the auto mesh option. So we have got piles as well. You see, it's auto mesh, and just select the plane that you want to mesh. So we'll start with the pile cap. So select plane, XY plane, and apply. That quickly meshes along with the pile intersection nodes, and also considering the proper connectivity with the abutment here itself. And also for the abutment, we can similarly go for plane type and just select 3 points on the abutment. Oops, sorry. And apply. So that's the abutment model. So that's a quick way of auto meshing the abutment and piles or any shell type of mesh in the structure. Okay, so these are some of the important aspects of the curved bridge modeling. Now, just to finish up, just touch up the precast infill type of section, which is a different section type because of the deck being exactly poured in the spaces between the closely spaced precast beams. Okay, so I'll bring up the model here. So that's the example of a precast infill bridge. And these sections, how to define these sections. So these are not standard database sections, so they have to be imported from AutoCAD. So I'll show you how quickly you can define this section in AutoCAD. So you go to section property calculator, meters, and just import from AutoCAD TXF. So that's the say one of the sections. Okay, so we have the lines. These section dimensions modeled as lines in AutoCAD, and we can simply go to material, define two materials. Say for slab. Okay, and also for girders. Okay, and then go to model section, composite section. We want this is comprising of 2 parts, so just type in 2 here. We can go up to 3 parts in a composite section. The base material is girder, apply, and then we specify which part is which. So add part name is girder, this is girder, and select all the lines representing the girders. So select everything, and I'll deselect the slab lines, apply, and then slab, this is part 2, slab, just maybe change the color to this one, and again select everything here and just unselect the members here, apply. Now we'll calculate the composite properties. So mesh size is 0.1, select one part, apply. So that's the composite properties are calculated. You can look at the properties here, and this is now ready for analysis. You can send it back to Midas, export, and save it as a TY section or whatever it is. You can save any section like this and then open them up in properties section, add composite as a composite general section, and say precast DY beams. Okay, so that's the section here. You can use it now for analysis. Just assign it directly to any beam or anything. To assign tendons to this section is just a simple way of first you can create a reference beam. So if I just save as okay. So let me just quickly cover up the final slide. So so prestressed precast infill bridge, the infill section modeling we have already seen. Orthogonal grillage was used for this section, so I'll quickly just show you while it's saving the model. So say new project, not extrude 15 meters. And we'll create the skew. So orthogonal grillage involves when you have the skew angle greater than 20 degrees. So let's make it -30. Move. Oops, it's in the X direction, Z axis. Select everything, extrude elements in the X direction. Sorry. Right. Okay, now for the orthogonal grillage, we can simply project the points here using the extrude function. Project them on this baseline, apply, and similarly select these points here. So, and this time the baseline is this one, apply. Now for in between, now we need to make sure that they are intersected properly, so I'll select everything and elements and intersect. So they are intersected, and just to fill up in between, go to translate elements and just measure the distance, 9, 8 times, apply. So that's your transverse grillage modeled, and you can start assigning properties or sections to different parts. So that's how quickly you can generate the orthogonal grillage. Okay, so composite action for composite infill beams is exactly same as how you do for composite in steel bridges. You have to differentiate between parts and see the results. So to just on the last note, we can also look at the design results for the bridges. So if I open up one model here, you can look at the results in different construction stages. Stage 0, let's say forces. So stage 0, so starting with beam diagrams, apply. You can see the pile forces here, so the soil structure interaction is being taken into account in the construction stages. And as we go on pouring the deck at different locations, we can look at the part-wise forces. So part 1, which is steel, that's bending moment in steel, and part 2, which is concrete, that's bending moment in concrete. Okay. And similarly, we can see other results. We can also look at the live load results from the moving tracer diagram. Okay, and do the design as well. So if it's composite steel design, can enter design parameters and different information for shear connectors and transfer stiffeners. Select the elements required for design and enter the shear connector information. And then in the result table, we have got bending resistance checks and several other checks, ULS checks and SLS checks. For the piles or the piers, there is reinforced concrete checks. So if it's the pier section here, select concrete code check, column checking. It will quickly run a pier check and give you the results in a graphical format. And you can look at the detailed calculation report as well. Okay. Similarly, for the composite steel section, we can look at the this Excel report, which looks like this. So that's the Excel report that is generated by the software in the design, for the design. Okay, there is another question. Can you show the beam and plate results at the same time? Because these are two different types of elements, so beam forces and plate forces, they are displayed separately. Beam forces and truss forces can be displayed at the same time because they are both line elements. But for the shell elements, you have to see it through the plate force diagrams. So that's where you see the plate forces, and you can then you can also sum up the plate forces to get the equivalent beam force. Okay, so that brings us to the end of the presentation. So if you have any more questions, I hope I was able to answer most of the questions during the session. If you have any questions, you can send us by email on UK support. Anybody who is also interested in any special training for any particular topic or project, we also provide bespoke training, in-house trainings by visiting your offices, and may also be web-based as per your suitability. And yeah, so we provide you with the full workflow of the project and show you how you can save time and money on a particular project. So this video will be uploaded on our YouTube channel, Midas UK, and you will be sent the recording of this video so that you can refer it later on. And if you have any suggestions for future topics or webinars, please let us know, and we will include them in our future e-learning series. So that's our email address. If you have any questions, please drop your questions here. And thank you for attending. Bye for now.